Electric field intensity due to infinite line charge. A line charge is extending from z is equal to minus infinity to z is equal to infinity along z axis. We assume that the line charge density of the source is known, which is represented by rho L. We consider the point under observation on the y-axis, and we assume that the position vector of the point under observation is rho arrow, which is a vector in the cylindrical coordinate system. We consider a small portion of the source, which is represented by dl, and the position vector of the small portion of the source is r1, so r1 will be equal to zaz. So we consider the position vector of the point under observation in the cylindrical coordinate system, which is rho arrow, and the position vector of the small portion of the source, which is in the cylindrical coordinate system as well. The vector which extends from the small portion of the source to the point under observation is r minus r1. We know that the electric field intensity at the point under observation due to a line charge is given by equation number 23. The electric field intensity will be equal to the integration of rho L dl into r minus r1 by 4 pi epsilon r minus r1 raised to power 3. So we shall use equation number 23 to find out the intensity at the point under observation. We know that r minus r1 will be equal to rho arrow minus zaz. The magnitude of this vector, which is extending from the small portion of the source to the point under observation, is equal to under root rho square plus z square. And the differential length of the small portion of the source is dz, as the source is along z axis. This is why the differential length of the small portion of the source is represented by dz. We put these values in equation number 23. We put the value of dl and r minus r1 in equation number 23. So if we put these values in equation number 23, the electric field intensity will be equal to the integration of rho L dz into rho arrow minus zaz by 4 pi epsilon rho square plus z square raised to power 3 by 2. You see, dz indicates that the only variable is z on the right hand side, and z extends from minus infinity to plus infinity. We need to integrate this particular equation. For the integration of this particular equation, we consider the right angle triangle we consider the right angle triangle in this diagram. Consider the right angle triangle in this diagram. You see, we consider this right angle triangle. The base of the triangle is rho, and the perpendicular of this triangle is z. The base of the triangle is rho, and the perpendicular of this triangle is z. So we consider this right angle triangle. We consider this right angle triangle. You see, let me explain this triangle once again. We consider this right angle triangle. The base of this triangle is z, and the perpendicular of this triangle is rho, right? So z by rho will be equal to cotangent theta. So z will be equal to rho cotangent theta. Definitely dz will be equal to minus rho cosecant square theta d theta. So the new variable will be theta, because we obtained d theta over here. When z is minus infinity, then theta will be equal to pi radians, and when z is plus infinity, so theta will be equal to 0. We put all these values in equation number 24. We put all these values in equation number 24. So let us put all these values in equation number 24. So the electric field intensity at the point under observation will be equal to rho L into rho cosecant square theta d theta into rho A rho minus rho cotangent theta Az by 4 pi epsilon into rho square plus rho square cotangent square theta raised to power 3 by 2, and theta is changing from 0 to pi. We simplify this equation. So the electric field intensity at the point under observation will be equal to rho L, the integration of rho L, rho square cosecant square theta d theta into A rho minus cotangent theta Az by 4 pi epsilon rho cube into 1 plus cotangent square theta raised to power 3 by 2, and theta is changing from 0 to pi. We know that 1 plus cotangent square theta is cosecant square theta. So if we simplify equation number 26, we obtain equation number 27. The electric field intensity at the point under observation will be equal to rho L by 4 pi epsilon rho. Then we have the integration from 0 to pi, and we have cosecant square theta d theta into A rho minus cotangent theta Az by cosecant square theta raised to power 3 by 2. We simplify equation number 27. Let us simplify equation number 27. The simplification of equation number 27 results in this particular equation. The electric field intensity will be equal to rho L by 4 pi epsilon rho, the integration from 0 to pi of d theta into A rho minus cotangent theta Az by cosecant theta. Equation number 28 can be written as the electric field intensity at the point under observation will be equal to rho L by 4 pi epsilon rho the integration of sine theta d theta into a rho minus cotangent theta az, and theta is changing from 0 to pi. So this equation can be written as the electric field intensity at the point under observation will be equal to rho L 4 pi epsilon rho. We have the integration of sine theta d theta a rho from 0 to pi minus the integration of cotangent theta sine theta d theta az. We know that cotangent theta is equal to cos theta by sine theta. So if we put the value of cotangent theta over here, which is cos theta by sine theta, so we will get this particular equation. The electric field intensity will be equal to rho L by 4 pi epsilon rho. The integration from 0 to pi of sine theta d theta a rho minus the integration from 0 to pi of cos theta d theta az. Let us simplify this integration. So we simplify this integration. We know that the integration of cos theta d theta will be equal to 0. Right? If we integrate, you see cos theta d theta, and if we put the limits after the integration, this integration will result in 0. So this term, the second term will be equal to 0. I mean the integration of the second term results in 0. And definitely the electric field intensity will be equal to rho L by 4 pi epsilon rho, the integration from 0 to pi of sine theta d theta a rho. And we know that the integration of sine theta is minus cos theta. The integration of sine theta is minus cos theta. And if we put the limits over here, we will get 2 over here. So we will get 2 over here, and we will get 2 2s are 4. So we will 2 in the denominator. So the electric field intensity at the point under observation depends upon these parameters. Electric field intensity at the point under observation will be equal to rho L divided by 2 pi epsilon rho into a rho. Right? So this is how we calculate the electric field intensity at the point under observation. You see, if we consider this infinite line charge inside a cylinder, such that this line charge is on the axis of the cylinder. So as rho is constant over here, the electric field intensity depends upon rho only. So as rho is constant over here, the electric field intensity on the surface of this cylinder will be constant. Similarly, if we draw a line parallel to the source as shown over here, the electric field intensity along this line will be constant. It will be uniform, because you guys can consider any point along this line, and the radial distance between the source and any point on the line is constant, which is rho. So the electric field intensity on the surface of this cylinder will be uniform. It will be constant. Similarly, the electric field intensity along this line will be constant. See, if we replace rho by r and a rho by ar, we can write down the electric field intensity with the help of this particular equation as well. The electric field intensity will be equal to rho L by 2 pi epsilon r ar. Electric field intensity due to infinite sheet of charge. So let us consider an infinite sheet of charge in the x is equal to 0 plane. You see, this sheet of charge is extending from y is equal to minus infinity, from y is equal to minus infinity to y is equal to plus infinity, and from z is equal to minus infinity to plus infinity. So this is an infinite sheet of charge which is located in the x is equal to 0 plane. This infinite sheet of charge is located in the x is equal to 0 plane. We consider a narrow strip of the sheet over here, and the width of this narrow strip is dy. This width, this strip is so narrow that it almost behaves like an infinite line charge, right? And similarly, we consider another narrow strip over here, and the width of this narrow strip is represented by dy as well. And the width of this strip is so narrow that it almost behaves like an infinite line charge. We consider the point under observation. We consider the point under observation on the x-axis. So this vector is represented by yay. This vector is represented by xax. So r1 will be equal to yay minus xax. Similarly, if this vector is minus yay and this vector is xax, so r2 will be equal to yay plus xax, right? So we know that the surface charge density of the sheet will be equal to dq divided by dy dz. You see, the differential area of the sheet will be equal to dy dz. This sheet is located in the x is equal to 0 plane, so the differential area of the sheet will be dy dz. So the surface charge density, which is the charge per unit area, will be equal to dq by dy dz. Well, you see, if we play with this particular equation, dq by dz will be equal to rho s dy. And rho s dy is the line charge density of this infinite line charge. Rho L is the line charge density of this infinite line charge and this infinite line charge. So rho L, which is basically equal to rho S into dy, is the line charge density of the infinite line charge on the right hand side and the infinite line charge on the left hand side. So we consider the infinite line charge, the strip on the right hand side. So we know that R1 will be equal to xax minus yay, and the magnitude of R1 will be equal to under root x square plus y square. AR, which is equal to R1 by R1 will be equal to XAX minus YAY by under root x square plus y square. And R2 will be equal to XAX plus YAY. The magnitude of R2 will be equal to under root x square plus y square. The unit vector in the direction of R2 will be equal to R2 by the magnitude of R2. So this unit vector will be equal to XAX plus YAY under root x square plus y square. Right? We consider the differential intensity at the point under observation due to the infinite line charge on the right hand side. So we consider this infinite line charge and we calculate the differential intensity at this point under observation. Okay, so the differential intensity at the point under observation will be equal to behaves like an infinite line charge, so it will be equal to rho L divided by 2 pi epsilon R1 into AR. If we put the values in this particular equation, rho L is rho S dy, right? And then we put the value of AR and R1 over here, so we get this particular equation, right? Then we consider the infinite line charge on the left hand side. We consider the infinite line charge on the left hand side and we calculate the electric field intensity at the point under observation due to this infinite line charge. So the electric field intensity due to the infinite line charge on the right hand side, on the left hand side will be equal to rho L divided by 2 pi epsilon R2 into AR, right? And then we add these two differential intensities. Well, we put the values over here. If we put the values on the right hand side, we will have rho S dy, and then for AR we have XAX plus YAY, and we have 2 pi epsilon, and then we have x square plus y square, right? So this will be the differential intensity at the point under observation due to the infinite line charge on the left hand side. We add these two differential intensities. So this is the differential intensity at the point under observation due to the infinite line charge which is on the right hand side, plus this is the differential intensity at the point under observation due to the infinite line charge, which is on the left hand side. And I have plus sign over here, by the way, right? This sign is plus. So if we simplify this equation, the differential intensity at the point under observation will be equal to rho s dy xax by 2 pi epsilon x square plus y square. So we obtain this particular equation. And in order to calculate the total intensity at the point under observation, we integrate this particular equation. So the electric field intensity at the point under observation, the electric field intensity at the point under observation will be equal to, we have the integration of rho s dy xax divided by 2 pi epsilon, and then we have x square plus y square, right? So dy indicates that the only variable is y on the right hand side of this equation, and it is changing from minus infinity to plus infinity, right? So we need to integrate this particular equation. So what we do, we assume that y by x is cotangent theta. So y will be equal to x cotangent theta, and dy will be equal to minus x cosecant square theta d theta. When y is minus infinity, then theta will be equal to pi radian, and when y is infinity, then theta will be 0. So what we do, we put all these values in this particular equation. We put all these values in this particular equation. We put all these values in this particular equation, right? So let us put the values on this particular equation. So the electric field intensity at the point under observation will be equal to the integration from 0 to pi of rho s x square cosecant square theta d theta ax by 2 pi epsilon x square plus x square cotangent square theta. We simplify this equation, so the electric field intensity will be equal to the integration from 0 to pi of rho s x square cosecant square theta d theta ax by 2 pi epsilon x square cosecant square theta. If we simplify this equation, we get the electric field intensity at the point under observation, which will be equal to rho s by 2 pi epsilon, and we have the integration of d theta ax from 0 to pi. And if we simplify this one, the electric field intensity will be equal to rho s by 2 epsilon ax. And if you look at the infinite sheet, the unit vector ax is normal to the sheet. So generally, the electric field intensity at the point under observation will be equal to rho s by 2 epsilon an.